So it's about 7:40, so let's just start. Okay, thank you all for coming again. So today, like always, our student seminar is for students to present and then hopefully learn along the way and make mistakes along the way too. Okay, okay. So audio is working. Okay, so an interesting thing is like from the first week onwards, like the qualification is in terms of degree, right, is the highest. Okay, and then it decreases a bit, and then up to hours is like the local global minimum. Okay, and then increases again at the end. So just bear with us. We'll try to present what we understand, and hope you enjoy. So today we are going to talk about projective varieties. It sounds kind of cool, projective. So, but before that, let's first do a review of what happened before. Okay, so in essence, like what are we doing in algebraic geometry, right? We are just just looking at the solution set of a set of polynomials. So just like any high school problem, if you have a list of polynomials, and then what your job is to find the solutions x1 up to xn. That's all it is. And then so some examples include like our usual linear algebra, right? Linear algebra is a special case of algebraic geometry, right? Just with degree 1 polynomials. So all the subspaces and stuff you do in linear algebra is a special case of algebraic geometry. Moreover, but of course, the point of it is going beyond linear algebra by making it a bit more quadratic and so on, higher degree. So for example, like a simple curve like y squared minus x is also algebraic set, or in this case, algebraic variety. So what in essence you're doing is just y squared minus x and solve for all xy. Now, one thing to note that this is the picture that we usually see in AT 101. But one thing to emphasize is we always work with the algebraic closed field, meaning we can just think of it as the complex numbers. So in reality, it's way more complex a bit. Yeah, so the graph is like a bit more hippie like that. So but that's just what we need to keep in mind. What we're actually working over is the complex numbers. But to aid ourselves in our understanding, we can first look at the real graph first to get a gist of what's happening. Okay, so that's a review of what happened before. So now we are going to our main topic today, which is projective variety. So before that, we'll motivate the idea of projective space. Okay, so now, all right, hope this is not awkward. All right, before that, now I'm going to perform a magic trick in some sorts. Okay, so I need some volunteers. Okay, right. So so ideally, it's like if they are unsure of what's happening, right? So first one. So what is this magic trick? So what you need to do is very simple. Okay. All right. Yeah. So just on this line, okay. Right, 我们选3点，就选3个点, right? Pick 3 points on this line randomly, whatever you like. Okay. Okay. Oh, so spaced out is so nice. Okay, and then should I call someone else out? Here. Right. Okay, thank you. All right. So next one, you can have a snack for coming out. Okay. All right. Same thing for the bottom one. All right. Randomly pick 3 points. Okay, there you go. That's someone trying to mess me up. Okay, I hope it still works. So, okay. So like in so this is something that the ancient Greeks did. So let's label these points A, B, C, and then this one A prime, B prime, C prime. Okay, should still work. So this is kind of combinatorial, all right? But so we'll join these two, A, B prime. Okay, join. All right. Oh, all right. And then A, B prime, and then we can join A prime B. Okay. All right. So this is a bit technical. And then after that, we repeat the same process. Okay. Okay. So do the same for A and C prime. Okay. All right. Kind of regretting using whiteboard now. Okay, but and then okay, this is the first intersection point we'll look at AC prime, and then repeat it again, A prime C. Right. Okay, so yeah, this is like the points were chosen randomly, right? By them, probably. So, okay, right. So like there are many geometry problems in high school, right? Some are quite boring, right? Some is like just find an angle, find some missing angle and so on. But there are sometimes some geometry problems that are just like meant to be. So this, I believe, is one of those. Okay. Oh, I did it. Okay. So VC prime. So I circled those three intersection points. And then the claim is that these 2 points by a miracle lie on the same line. Right? Okay, we're not done yet. All right. 1, 2, 3. Okay. Oh, finally. Oh, so right, this this is the magic trick, right? You can in fact do it ideally, I mean not ideally, for any A, B, C, A prime, B prime, C prime. So let's find a better drawing over here. Okay, so it's over here. Okay, here. All right. So this is the exact same thing as just now, right? So I can randomly pull A, B, C around. Okay, and then it still work. And then maybe you think it should be A, B, C, or and not A, C, B, but that's also not the case. So for example, I can pull it over here, pull A over here behind A. C, I can move it around between A and B. And then you can see that it still works, right? All those points still lie on the line of the intersection points, no matter what you do. Okay, right? This thing is called Pappus theorem, right? As I said just now in the ancient Greek time. So given any two lines, right, randomly pick ABC and A prime, B prime, C prime, and then do what I said just now, and then it will be a collinear, right? No matter what. Okay, that's a nice thing to prove. Maybe in high school you would actually no, that's quite complicated. But maybe if you're bored, maybe you'll try to prove it by yourself. But there's one small problem. Like, what is that problem? Since I said ABC could be anything, right? So what happens if the case for this? Over here, A and C. Okay, look at A and C2 and A2 and C1, right? We will notice that they are parallel, right? So over here, right, C2, at least I try to make it parallel. 2 and then A, C2, C1, right? They are parallel. So what does that mean? That means they probably don't have an intersection point, correct? Because that's the definition of parallel lines, right? They don't intersect. So, but one interesting thing, okay, these 2 points are still okay, right? They can form a line, but okay, so as you can verify just now, right, A1, C2 and AC1, A2 is still parallel. But one interesting fact is to notice that although, okay, maybe, okay, that third intersection point disappeared, but, right, notice it kind of looks like A2C1 is parallel to the line formed by the intersection points, okay? Okay, just maybe a coincidence, or maybe not, but yeah, they are just somehow parallel when that other intersection point disappears. So that's okay. An annoying fact actually, if you wish to prove a theorem, right, you have to state a lot of conditions first, right? They are not parallel and so on for this theorem to work. So, but anyway, those are special cases probably, although, yeah, it's annoying, right? But you know, people move on in life. But so, but there's a way to a way to resolve this, right? Because being parallel, right? What does parallel look like, you know, in real life, IRL? Okay, when you're in the north-south highway, right? When you look down at a road, right? Or in art class, it looks like that, you know, although these two lines are parallel, right? And then you don't have to assume the curvature of Earth, okay? If locally, right, 80 kilometers basically flat. Yeah, so, right, yeah, two parallel lines, right, on a flat space, right? It still seems like they still converge far away, right? Yeah, so like this fact is kind of like from art, right? Like usually in art class, maybe you want to draw something with a perspective, you would have like just draw two parallel lines or a horizon, right? A horizon, okay, and then uh go and then this will be two parallels converge at the horizon, and then you can do a lot of things here, right? For example, if you want to draw a checkerboard with a perspective, right? You just draw a lot of these lines, right? And then this is, right? I can get A plus in art class already, right? So yeah, this is something in perspective. So like in art, there's this idea of parallel lines converging at infinity. So okay, maybe this is a better picture. So this is actually a parabola on the flat plane. Yeah, it doesn't look like parabola, but since those two lines, they usually go to infinity, right? In art world, right, it will converge, it will look like they converge at that point. Okay, so at least in art, right, parallel lines can converge at a point at infinity. Okay, so maybe we have a wish list, all right? Maybe if lines could actually intersect in infinity, our previous theorem would be correct? So for example, like this one just now, right? Although they are not that intersection point is not on the plane over here, but if somehow it intersected at infinity, then if the theorem will still be true, right? A3, C3 will still lie, and then B3 will still lie on the same line. Okay, so right, maybe if parallel lines could actually intersect infinity, our theorem will be correct. Okay, all right, but we have, so maybe this would serve as an motivation to define something, correct? So like if we try to define something more rigorously, right, we find inspiration from nature, okay? So how do we find inspiration now? So what happened, what were we doing over here, right? When we were looking at the road, converging at the horizon, right? We were standing on the road and then looking down like that. Okay, so something like this. This is my diagram with very good captions. Okay, so this bro is standing there and then he's looking down at the flat plane like that. Okay. Standing on the plane, yeah. So and then looking down. So maybe if we could somehow make vigorous the idea, so actually his body is not important, just the head. Okay, so and then so head, all right. So if he could look down, so this is actually what's happening now, right? Let's simplify the problem. He's looking down, and those are his fields of vision, those straight lines, and somehow capture the idea of infinity. Okay, we will make vigorous this idea later on. Okay, but before that, let me just summarize the intuition of what we have now, right? This space that contains infinity, we call it the projective space. Hopefully, it's quite motivated, the name, because we are kind of like above and then we are projecting. Yeah, okay. Yeah, so, and then, yeah, so points at infinity. This space somehow contains points at infinity. Okay, and then like art class just now, right, parallel lines converge at infinity. And lastly, right, to describe these points at infinity, we need to go a dimension higher, right? For example, we want to look at a 2D plane, right? We have to be a dimension higher to look at the infinities. So, like these 3 points, right, we need to go up a dimension, right? Just keep this at back of your head first. Okay, but before that, right, because of audience, right, so I have prepared applications, right? Surprise, right? So applications. In fact, I was also quite surprised. And then first one, Kluger coordinates. Yeah, probably will go in more detail next week. But Kluger coordinates is used in robotics. I don't want to talk about a full story, but essentially, the motion of something can be described by a line, a random line in 3D. Okay, and then to describe a line in 3D, we can use projective geometry. Very naturally describes it. And once you do that, you can make your computations more efficient in some way, right? You can have a look at the paper if you want. And then also interestingly in physics, right? I was just randomly searching up, but also not that surprising, right? It has you can use it to understand special relativity, but it kind of makes sense because like the speed of light is supposed to be something you can pass. So like something like a line at infinity, a point at infinity. But okay, and then lastly, I'm not sure about this QM part, but I have heard of projective Hilbert spaces, so I guess that could be useful there. But also interestingly, Paul Dirac, like when he was developing quantum mechanics, he usually thought of it from a projective geometry point of view, right? You can all read it up later. So this is, I'm just trying to say this idea is not like very out there or anything, right? It can be applied because it stems from a natural idea, which is looking at something from a perspective. Okay, but okay, these are application, okay, very good. But this, I believe this is what's the selling point of what projective space. Okay, there are not many theorems, that can like, prove a higher entity exists, So like, but this theorem does it. So what's this idea, this theorem? So if you can recall from fundamental theorem of algebra, right, that's a big name, but it's a fact that we know from high school, right? If a degree of a polynomial, right, is n, okay, then its number of solutions, the number of solution is n, counting multiplicities. Right? If you forgot about definition of counting multiplicities, it's like for example, x minus 1 squared, right, equals 0, right? Although the solution for this is x equal 1, but it's squared, so it's like kind of repeating. So that's why we say counted with multiplicity. So this will be like two solutions, two of the same solutions. But anyway, this is the fundamental theorem of algebra. We all use it in high school, right? The number of solutions is exactly n, but of course you need to assume x is in the complex numbers. Okay, so this is a nice fact. But interestingly, this fact also extends above, right? This theorem is called Bezout's theorem. So what it's saying is C and D algebraic curves. So what does that mean? If like you have two algebraic curves, meaning fxy equals 0 and gxy equals 0, right? So essentially fxy will look like something like maybe x cubed plus x squared y 5 or whatever, any of those kind of polynomial things. And then you solve for the intersection points. So for example, these are intersection points between algebraic curves. So these are between lines, and then the circle and line and so on. And then ellipse and ellipse. So an interesting fact that one may observe is that, okay, for the ellipse case, what describes an ellipse? Ellipse, right? That one is also a nice high school fact. Right, ellipse is described by a quadratic polynomial thing, right? So like x squared plus 5xy, y squared, and then plus whatever you like, and then equals 0, maybe a constant here, right? This will probably, hopefully describe an ellipse. And then this polynomial is a degree 2 polynomial, right? So this degree of this is 2. Okay, so so over there are 2 degree 2 polynomials over there. So when you intersect them, right, there's just 4 points, right? Sorry, had the Malaysian came in, right? So this one has degree 2, right? This one also has degree 2, right? Which is exactly 4 points, right? Quite nice, quite interesting. Okay, maybe we need to check it again, right? A circle and a line, okay? A circle and a line, a circle and a line, okay? The circle has degree 2, okay? The line has degree 1, okay? And then you multiply them together, 1 times 2, 2. And then there's also exactly 2 intersection points. Okay, cool, nice fact. But of course, there's also the obvious problems, right? We can obviously separate them, okay, far away. make the ellipse to have no intersection at all. But that's the problem with the view picture of this, right? I always emphasize incomplete because we need to work over an algebraic closed view, which is in this case the complex numbers. So actually, in fact, if you work over the complex numbers, it's better, right? You get more solutions, but unfortunately, right, it's still a less than or equal. So given algebraic curve of degree m and degree n, right, the number of intersection points, right, right, is at most mn, okay? Most, even if you include the complex numbers, right, x, y in the complex, okay? It's still less than or equal to. And then probably, okay, it's probably good enough, right? You can pack your bags. But interestingly, right, some person, right, well, he just bothered to try it for by looking at it as perspective. When you look at it in a perspective, meaning like the case just now, so that means considering points at infinity as solutions too. Right? Once you do that, just for some reason, right, you look at the plane, these algebraic curves at a perspective, you instead of a less than or equal to, you get a equal to. Okay? Right, equal, like it's not going to be less, it's just always going to be equal, right? Of course, again, counting multiplicity, but yeah, exactly equal to mn, right? Just by, respecting nature in some sense, right? By looking at it from perspective. So in fact, with this, right, we can give a proof of the fundamental theorem of algebra, right, without topology. So suppose you have a degree n polynomial, right, which is the usual xn, and then you plus so on, right? And then what is the solution to a polynomial equation, right? You have a polynomial, right? You want to find its roots, right? It's equivalent to intersecting it with the line at x equal y equal 0. Okay, so this is a line, right? This has degree 1, right? Our polynomial has degree n. So yeah, the fundamental theorem algebra trivially follows, right? From this. So the number of intersection points are at most n. So Bezout's theorem is actually, in fact, can be thought of as a generalization of the fundamental theorem of algebra. Okay. So like just by considering points at infinity, we somehow made it all perfect, right? Somehow everything works out. It equals to mn. So with that, that's hopefully sufficiently enough motivation, right? Compared to a normal math talk. So we'll now go into the precise definition of what a projective space is. Okay.
That's a very long motivation.
Yeah, not standard.
Very outstanding. Well, I hope the motivation can keep you guys keep you guys awake. Okay. And I'm here now. We are going to talk about the projective space that he's talking about, where the point in this space actually intersect at infinity. So projective space, over as usual, we will consider K as an algebraic closed field, but in the next visualization and all, we are going to do it in real number because it's easier to visualize. In complex number, you only can do a very low dimension. So yeah, I need to do the board. Where did you throw the thing? So before that, hello. So before that, I will talk about the elements that actually lives in a projective space of n dimensions. Okay, the elements that lives in the projective space is actually equivalent classes of points where, okay, if you look at there, x naught, x1, dot, and xn. has a relation lambda x not, oh my god, and yeah, for all lambda in K, but not zero, okay? So in a projective space, the point in projective space is actually a line, okay? For for a K, P, n dimensions, the point in here is actually lines in your A n plus one. So we add one dimension to the space. So yeah. And yeah, just some notation problem. So the elements of KPN, as you can see, they are called homogeneous coordinates, and we write it instead of the comma, we write the, how do you call it? Yeah, thank you. Okay. So this is how it looks like if we um, take a look at RP1 and we put it in A2. So just like the motivation just now, you are the stickman here. You are the stickman here, and all your vision, all your lines of vision is all these lines. Of course, I didn't cover everything. Okay. Then you are sitting here with your head only. Okay. You are looking in the front. You're looking at the front. So if you imagine that there's a line in front of you, so your lines of vision that intersect on each point on it is actually an element in your projective space. So in P1, it's just a line. It's just a line. But yeah. So but if you want to get it, it will be something like in A2. In A2. So your field line is like this. So it's like you're seeing from here. So your curve here will be a line in P1. And this is from the perspective of A2. Okay. But before we talk about what happens when you look 90 degrees towards your right or your left, we will not talk about that first because that's where the infinity actually exists. So yeah, in P1 is actually not really that complex. So we'll take a look at A3. So it's still the same thing, but now your projective space, instead of a line, now it's a space, it's a plane where your vision now, just now you can look from left to right. You are still in the middle here, but now you can look left, right, and up, down. Okay. So, and the same thing is that the intersection will be the points in your P2. Okay. I think this is pretty easy, I guess. Okay, this is something that I want to talk about from the jazz. I think it's pretty interesting. So it says that if you take the set of UI that the equivalent classes points in your PN space, and you take one of the AI, then you fix it as a constant. And you fix it as a constant, meaning that you're taking a certain level, just like just now. The UI, if you take it as, so this is X, Y, Z. So if you take it as Z equals to 1, that means it will be a bijection from the lines. So you can see that the lines only intersect at the plane Z equals to 1, each one point at each line, right? So this is like something like you are looking and then you set how far that you are looking. Okay, it's like I'm looking in front, but how far do I want to look? Okay, I can look 2 meters away, 1 meters away, and and you can look at yourself. So what happens when you look at yourself? Okay. And interestingly, when you look from Z goes to 1, and you look Z goes to 2, and each of them will still be isomorphism between them. That means your lines goes infinitely far, and then they will only intersect each AI that you choose, not AI like each depth that you choose only once. Okay. And actually, if you look at only the points at the plane, and you omit, if you omit one of the coordinate, that means like, okay, in 3 dimension, when you cut the 3 dimension, you get 2 dimension, right? So this means that like you omitted the z dimension. So now you only have a 2 dimension plane. So it will have a, so in A, like a projective, the projective space is like like P2 is like there's a relationship between A2, but P2 has something more than A2. Okay. So this is just something else. Yeah, this is what I said just now. You are taking all the, how far that you're looking, you are cutting it, or you are putting a paper on it or whatever, and then you see the intersection, they'll all only intersect at one point on each line and each plane. Sorry. So as I said just now, the difference that between a projective end space and a affine end space is that the projective end space includes the points at infinity. So how do we say that? What is the point at infinity? Okay. So in this definition, it says that the hyperplane at infinity is defined as the point at infinity whenever you look at yourself. Okay, you don't look front anymore. You take like just now. Just now, you look at the intersection of plane and z equals to 1. So when you look at z equals to 0, that means the stickman head where you are right now. You look at yourself, and then you notice that all the lines that are intersecting on z equals to 1, okay, actually doesn't intersect when z equals to 0, because everything will be at the origin. And then in projective space, there's origin is excluded. So the only points that you can see in when it's intersecting and z equals to 0 is that when you look at the parallel to the planes, which is all the set of points at infinity. So the set of points at infinity. So wait, tired. Yeah, I actually stayed up until 3 o'clock last night doing the slides. Wait, let me think. Yeah, I think because this is only like we're trying to make it like not really serious and not really like hard like the other people have done it. Not this first, not this first. Yeah. The examples is in the next slide. Yeah. So someone told me to define this definition as the next speaker wants to use it. You want, do you want this?
I don't want you to just explain
Huh?
Sure.
I mean, the definition is not really like something. I mean, it can be complicated, but we are only taking the easiest one. So now, if you like the graph, denoted by GR and KP. NK means that you are in n-dimensional space, and then you take the k-dimensional subspaces as the set of elements in this thing. So that means either you are taking lines as elements, or you take k equals to 2, that means you'll be taking things as the set, or you take 3 dimension, I don't know how that looks like. Maybe cube, I don't know. So it is very obvious lah. Okay. The GR n+1, and you take 1-dimensional lines, which is the line that you guys see just now in n+1 dimension, is the projective plane space. Yes. So you want me to stop him? Yeah, you guys wanna like take a 10-minute break? 我没有手表。Yeah, no problem. Yeah, we'll take a 10-minute break. Thank you.你要一下讲
我说我们现在那个intellectual 我们加个前沿加上它的法律对，我们还要加那个的话，
如果要讲，要讲那也不风险。
我知道你比较顺的，你们那个是那个简单的用字而已。这每一个就把里面的名词全部列在里面。对，找那个对，要在哪边对，我也是可能与是对应的，但是我们这边觉得比较很好看。我知道我的会比较但是你们能看得见啊？那个应该是其实目前然后我大概然后到时候做完以后，然后我再我们所以你干嘛这么做？
让我发现
那时候呢，
then so we use version on this side. And you can read that more easily on seminary. It's also for the that just thinking of it because I told you that at least there's something that's like, but yeah, it's写个了，我打厕所，那个，他只说那个，他就是一个昨天那个学热水，一个上水一天在那去弄，他的那个啊，他这是出来了，他一个 describe 就可以这样，这还是一个很方便的，可以直接。IE 来自的有点你看这个对这个。
我是有6边，在一个 R2里面，这个 R2的嘛，一定会一个 R2 的嘛，在一个导购里面，所以导购里面，你的反应嘛，你的反应对。It's more fun if you want 就是这样，或者是因为你假设你了解导出去了，所以那现在讲，假装没有这讲，不要想，然后我那个家父的可能没听过，给我们理解一点。我姐你看老师写的说不过给。哎，不是不是，大家知道。Bisa kasih我认识的东两个都比我学的就200。中国那些大学就没有，也是聪明。他说总共100到200个人，我们学校有200多。稍微让大家都会重点也是要多一点。要来在课学习那些关于我们最后主要就是正常的，因为都是我稍微是他我看一下完整，还有灵感。对啊，我觉得你可以写感觉，我要看完了。像，我觉得小题，老师来就是从这里开始。
对来讲，
不是主要你们这句话，他画了时间讲不来。确实，哇，你们下午3个月，没有不然有点贴着一阵。 首先想跟我讲一个本来的第二名，我还要讲一个，需要我讲一后面，然后前面是我，你还要让我讲 Grassmania，我怎么可能讲得完呢？It seems possible. 没有啦，然后还没。我都已经准备不是 theory， 就是第二个 point 里面是。我感觉第二个 point 这么一个定调。我猜了一些。这个关系。其实这个表示它可以理解那个 R 意思。它是在看资料的。你看你们都讲两个方向。对，然后那个就是现在讲是这样一个标注来的，就在这两个上面。你两位知道吗？哎，你们不讲不对。你跟我讲不对的 brain， 我需要有 brain 会想法，有 brain 还没有讲，那个错了，那个把这些其实刚才你还有一个是选往 A 其实你可以想象，把一个 plan， 这样就可以把所有，比如刚才跟你讲，刚才有一个 plan， 它看不到这个里面，但是它另外一个 plan 的时候，里面就非常大，所以用不同的 plan 把这个整个可以组装起来。不同的 UI 呢，你写出面。那个 UI 就是一个是单一个字，对，因为有一个 plan 或者一个 line 是看到那个另外一个 line 想要那个新物件，单方向到另外一个。那如果你用约起来的话，那你就看到了，你的 UI 对啊，没有，关键是一个 UI 嘛，看不到一个像我们这边是好，但是另外一个 UI。但是你就看不到那个，那你运起来说，所以这边就会这样。那你学的原理下来，你换另外一个方向的来，因为 the nature of 那个先是 the nature of 装。对于是要走它的切合，对，因为它从小是那类型，你该就是像你讲的，但是这条线跟很多听众来说，他不是从那时其实看不到另外一个。那是他妈妈是吧？谢谢。
有我吃了你的那个饭，好像不怎么爽。真的。对，我现在有点肚子不爽。我知道，我知道我可以回来，只是我现在肚子不爽，怎么办？
你敢吃？
这样贴心啊！
把谁肚子吃？
哎，就。Yeah, before I'm gonna go and talk about an example for the hyperplane, but before that we need to define some stuff. So the first thing is the homogeneous polynomial. So a homogeneous polynomial is such that every term in the polynomial has the same degree. So you want an example? It's not okay. Example. Okay, let me think. You.
Polynomial in the line picture, for example.
Oh yeah, sorry. Wow, I'm so smart. Wait, okay, good. Oh, I don't need to write it.
Excuse me also.
Actually, all monomials are homogeneous. Right, all monomials are homogeneous. Yeah, for a homogeneous polynomial, of course. So if you want to verify if what you call a polynomial is homogeneous, you can sub the x into lambda x naught, I mean to each of the coordinate, and if you can factor it out like this, that means it is a homogeneous polynomial. So one of the example is this one. So you can see that the degree is same. So this is 3, 1 plus 2, 1 plus 2, and 3. So it's 3, 3, 3, 3, 3. Then you can factor out your scalar multiple lambda power 3 times by the whole thing. Okay. So this is just the definition about homogeneous polynomial. Yeah. And then another definition again. I'm so sorry, I'm not doing any like a lot of proofs or whatever. Maybe next time I'll add. But it's a lot just definitions and whatever. So this definition is about how do you homogenize a non-homogeneous polynomial. So this is your original f, which is not homogeneous. And then if you change the coordinate, you divide it by a new term. So this, the whole term only consists of one x1, x2 until xn. And then if you include another new term x naught, divide by them, not zero of course, and then you times by the x naught power d, and then you get a new homogeneous polynomial. Okay, so whether or not you want to trust me, you can try. You can try yourself. Okay, you take any non-homogeneous polynomial and do this, you'll find that it turns into a homogeneous polynomial. Okay, yeah, you can try yourself. Example. Got example. What you want? Give me a polynomial.
Maybe you can define how to do.
Hey,
Your favorite polynomial.
what's my favorite polynomial? What's yours? Ah, what's your favorite polynomial?
So, what was that Odell's equation? So y squared,
Wow.
right? X cubed, and then it was plus 7, yeah. All right, and then sorry. All right. Yeah. Okay. Yeah. Okay. Yeah. So okay. Make this homo.
Yeah. Oh, just kidding. Just kidding. Just kidding. Just kidding. Just kidding. So we will add another coordinate. Let's say z. Okay. So you get something like this. Yeah, 7, 0, and then you need to times the whole thing by power d. So this is 3, right? 3 or 2. 3. Sorry. Yeah, Allah. And times and blah blah. Get this, and then it's done. Wait, sorry. Yes.
You need the zero.
And don't use 0 also can. You want 0 also can. But if the 0 is later. Yeah, then yeah, you can verify that this one is homogeneous or not. Of course, it is homogeneous. 1 plus 2, 3, 3. Yay! I thought this was supposed to be done by Okay. Yay, example. So this is from actually one of the motivation, the art perspective, like the parallel lines that leads at infinity. So now we are doing it in the math way. Yeah. So if you consider a family of parallel lines, I did not use y and x, I use x1 and x2 in this case, because I want to add x0. So same thing, you homogenize it. This thing is not homogeneous, it's not homo. Okay. Wow. Yeah, and you do the same thing, x2. Times everything. Yeah, you run yourself nothing. X not C. You can see, move everything there and you get the thing. So just now, the hyperplane infinity only happens when you choose your x not to be zero, meaning that you're looking onto yourself, so you can find all the points at infinities. So you take x not equals zero, then you will be left with this x2 equals minus n x1, which is also a line. But this line is in your projective space. So yeah, and then this is what you will see. This is just two lines, like how I defined just now. Two lines with the same gradient, and then when you look at it in the A3, that means you are going into a projective space P2. You actually see that the line intersect at infinity, just like the perspective art thing. Okay. So in fact, for any m in that direction, they will converge to the point at that direction. Okay. So this is the main difference between an affine and this and the projective and space. Yeah, again, this is in real. So just for the visualization. Yeah, now we're gonna talk about the projective algebraic set, which is when you have a set of homogeneous polynomials and then you figure out the zeros, and then that will be your projective algebraic set. Tiring. But before then, you need to notice that we need to take polynomials that are homogeneous or not. It doesn't make sense. So if your polynomial is not homogeneous, that means that let's say this is not a homogeneous polynomial. So fx, let's say if it equals to 0, then for the same x, if you times by lambda, it might not be, the zero set might be different. But if it's a homogeneous one, so this is actually equals to, if you times by, then this is still 0. So everything will still be 0.
Like lambda to the degree of x. Yeah. But also you wanted to write.
Oh yeah. Yes. No, I'm just like showing it like you can take it out and then it will be 0 again.
Lambda.
What? Where?
There's capital F and there is small f. Yes, I guess capital F of x is f from small f. You're using capital F
and small f.
Uh-huh.
Then what should we explain the capital?
Oh, I'm just differentiating between the homogeneous and non-homogeneous. Yeah.
Okay. So
Yeah.
probably you wanted to write capital F of lambda x. Yeah. Okay.
Okay, I will delete everything. My brain is not working. It's good, right? No. You add it, come. My brain is not working. I'm on sleep deprivation. Yeah.
Sleep is important.
Yeah, please sleep more than 7 hours. I slept for like 4 hours. It's not enough. It's definitely not enough. Yeah, if so now that if we consider homogeneous polynomial, that means you can consider points in the projective space as no set of the polynomial because it is homogeneous. Just by the relation, everything is still 0. Okay? This is the definition. Still definition. Yeah, another example. Do you guys want to see? You guys want to see? This explain. Explain this one. The interesting thing that we homogenize it, like how we do. Let me write it out again. So if we have x1 square minus 4 x1 x2. So if we homogenize it, then you get this yeah. And you get the same thing, like x1 square minus 4 on x2 minus 3x2 square plus 5 times x0 square. So if you let it be 0, then we want to find the projective algebraic set. So if we set x0 equals to 1, it doesn't matter if you take 1, 2, but don't take 0 because 0 is the points at infinity. So if you take 1 to make it simple, you have the same things. So if you solve this polynomial, like how you solve it in high school, you get two solutions. One of it is this one. So that's I think that's a typo. It's not problem. Yeah, it's a typo. So you have solved that the x1 will depend on x2. Okay, and then you choose your x0 to be 1. So in projective space, the points in your projective space you split into two because you have two different solutions. Yeah, you guys want to see in the thing? 7x squared minus plus 2x2. Yeah, hey, you come. Thank you.
First coordinate is actually.
Oh, no, this is the x0, x1, x2. Yes.
Please speak.
S0 is free.
I mean, your one you can take anything for it. So it's like one class.
You pick X you would be one.
Mm-hmm.
But you didn't pick X2.
就 yeah，这个是 free 的。
Yeah, so
Could be X2. Yeah.
should be x2.
Yeah. Because if X2 is 1, then your X will substitute at 1. So become a positive.
Yeah.
You swap them. Yeah.
That's fine.
Okay.
Yeah, this is just how it looks like. So when you take z equals to 1. So I'm not, please don't turn the thing.
Okay. Right.
Because
Okay.
so you imagine the purple plane is that one. And then the blue, the green curve, that two solutions of yours. So it's like a curve in a projective plane. In our projective space. In projective space, you'll see this as the zero of the polynomials. Yeah, so it is like you are looking here, looking like this, it's like points. So the whole thing actually looks like this. Here comes the. Is it this one? Press it.
Okay.
Yeah, the whole thing looks like this. You see, that's why I told you to not turn it because
Oh, okay.
the line is not actually an exact one. So this is a false visualization. So please don't turn it. Yeah, it looks like this. So when you look at Z1, you can see you can see the lines like this, the zeros. Just like projecting on it. Yeah, how to switch it back.
Okay.
Oh, I have it on here. But I know why not. I can turn it. Fun. So another definition again. The projective variety is actually the almost same thing as the projective algebraic subset, algebraic set. But in this case, is that you take a subset and then you find irreducible polynomials, homogeneous polynomials for this zeros. So in short, it's just an irreducible projective algebraic set. Okay, another typo here. Yeah. Same, huh? News.
All right, thank you. So at least, so now we have a few of examples. Hopefully, you can vision and think of projected varieties in a more concrete way. So we are just going to repeat what we did in week 1, right? Which is the goal of algebraic geometry, which is to find the correspondence between algebra and geometry. So this is what happened last time, right? So the relation between algebra and geometry, right, with a lot of proofs and so on that our that Ryan helped us. So radical ideals correspond to algebraic subsets. Okay, maybe should what I find, yeah, I find. So add a find with everything. So okay, maybe we should talk about radical, right? I probably forgot. So the radical is right, of an ideal, right? Okay, this is a factor form, and then so this is given by f to the r, right? And then r is in n, and then all these f are from the ideal itself. Okay, so essentially just take whatever all the polynomials in your original idea and then raise it to a power as high as you want, right? This is like related to the multiplicity thing, in fact. So okay, that's a revision. So yeah, okay, V is the zero sets, V is the zero sets, right? It sends from 反了，so
要 definition 反了，
哎，
应该是 F 的二次方属于，
我
应该是 F 的二次方属于 A 的 F。
呃
With the BF such that
Oh, yeah.
power of R is
yeah, sorry.
Some power of F is in the original. Yeah, R is in R.
Yeah, sorry, yeah. So yeah, I slept at 2, not 3. Yeah.
No, I sleep at like 3:30 somewhere there.
So okay, yeah, that's radical. And then yeah, so that it corresponds to algebraic subsets and then so on, right? These were nice proofs in the last lecture. And then I goes the other direction, right? So if you have an algebraic set, right, or just a subset, right, you can go back to the algebra. It's meaning like all the polynomials that satisfy like equal 0 at those points, right? That's going backwards. Okay, so this is how we go back and forth. So what we want to do is the same thing here. Okay, so we want to do this in projectively. So algebraic subsets of Pn, and then what does it correspond on the other side? So basically, we just need to refine all our definitions, and then we can also kind of prove the Nustellensatz for the projective case. Okay, so we do the same thing. Okay, so V affine, right? What does that refer to? That just refers, for example, for the 3D case, right? So 3D case, we have like 3D case, and then we want to use 3D and then view a projective plane. So, oh shit. And then something like that. And then, so for 3D, we want to view 2D. So for this case, V affine refers to 3D space, this case, and then VA without affine refers to 2D case. So, but it's exactly same definition, right? Just how you define when something equals 0. So in fact, that's this relation between V affine and VA, right? Which is the relationship between projective space and so on. So so essentially, like what we did just now, right? We have find projective space. Okay. So yeah, we have a projective space. So we identify the lines with the points on the plane. So like these points are identified with the line. So that's what we are doing. We are creating an equivalence class. So for example, a point on P2, okay, let me go back there. A point on P2, right? For example, a point on P2 on this plane, right, corresponds to this line, okay, and then so on for all of that. So that's basically the definition of it over here, right? VA, if you want to describe projectively, just quotient it by the perspectives, and then you get all the lines and so on. So now what we want to do is find out what kind of ideals it has to be, right? Over here we say radical ideals, but in fact that's not enough, right? We need something more, right? Because of that condition, right? Because it's identified with the lines. So so it's like this. Like because for any points, right? They are all these are the same thing. So x naught, right, up to xn, right? They are the same as cx naught up to cxn. Okay, and then So ideally, right, what we want is if f is inside V alpha, then f cx naught as Cn should also be V A, right? Why? Because these are supposed to be the same thing. So that means like they should also satisfy the same relation. So we do the same thing, right? So what does it mean to be inside VA, right? It means that this equals 0 and then this implies this equals 0. So let's just look at that condition and try to work with it. What does that reduce to? So, okay, maybe we'll take an example. Okay, fxy, yeah, so f just x1 and x2. Okay, so maybe right, we try to make it to cubic, we have to a fourth, and then this doesn't, it's not homogeneous yet, so we just do this x1, x2 squared, just random, okay, x1 cube, and something like that should suffice. And then what we want is when you substitute in cx1, okay, cx2, okay, so you take it out, I should maybe include more components, x1 x squared, x2 squared. Okay, so like, okay, we substitute c-ins, the c-ins, and then we just do the algebra again. Okay, and then, but essentially what happens, right, you can factor the c's out, yeah. So, yeah, I should type this out. So, or maybe not. Okay, so we factor it out, c to, okay, well, yeah, it's not homogeneous, yeah. Right, so yeah, C4, x1 4, right? Yeah, that's related. So in fact, the A's doesn't have to be homogeneous yet. So C cube, okay, x1, x2 squared, and so on. Okay, so one thing we can notice is that the powers of the C, there are some repeats. Okay, for example, over here, okay, over here. Okay, okay. So might as well group them together, right? So x1 to the fourth, and then x1 squared, x2 squared, yeah. And then we have c to the fourth, and then repeat x1, x2 squared, and then plus x1 cube. Okay. Okay, so in fact, there's a definition for these parts, right? Since over here, notice, right, they have the same degrees, right? They are homogeneous in these local parts. So we will like define this as, right, this is F, right? This is F for the degree 4 homogeneous component, okay? Similarly, right, this is the degree 3 homogeneous component of F. Okay, so what did we say just now, right? We want this, right? Also, it's true for all C, right? Yeah. So that statement is supposed to be true for all C. So like okay, right? Equals 0, right? Then this has to be true for all C in the multiplicative form of the field. So yeah. So and then. Right, this must be true for all C, and then this and this and this. Okay. So, right. So now you can just look at C as just a polynomial in C now, right? These are coefficients, right? Since this is equal to 0 for all C's, that means, right, you can argue it maybe with fundamental theorem algebra or so on, or maybe linear algebra will do. But that means these homogeneous components, right? Since it's true, since this is true for all C in the K, right? That implies that these parts also must equal 0, right? The only polynomial in C that can satisfy this relation is the 0 polynomial. Okay, so right, that's an example. So right, so written out more generally, okay, maybe we can just write it as like this. Okay, just rub off those parts. Yeah. So right, in general, a polynomial can be written as a sum of its homogeneous component. Right, makes sense. So like any polynomial f, right? Just group the same degree terms together, right? D minus 1 and so on. Just group them together, right? This is not too special. So fx1 and then so on, right? Oh, I forgot x now, but okay. So these can be written as that, okay? And then by the same logic, okay, repeat, okay, this must we substitute cx naught, okay, and cxn, okay. And then what we arrive, right, by the same argument just now, right, we arrived that at for all these, right, fd, right, plus fd minus 1 and so on, all these. So for all these that were considered, right, fd must be equal to 0, okay? And then this is also, what does that mean? That means what, like over there just now, fd must be in the 0 set. That's the definition. So v of factor a. So this is a restriction on our ideal, right? So over here, right, over here. So that's the v the other way. So since we want that relation to be satisfied, since points are identified by x naught to xn is identified with cx naught and cxn. By this restriction, right, we deduce, I guess, deduce the definition, which says, which for a greater ideal, right? So this ideal basically satisfies the property that I just said. So, right, if f is inside the ideal A, so if f is inside the ideal A, right, A is said to be a greater ideal, right? If f is inside the ideal, then, right, fd, the homogeneous component for the is also inside that ideal, right? And then if that's the case, this A is said to be a graded ideal. Okay, so let's see, right? We have time. Huh, do you want proof? So in the book, what you want to see a proof of? I did not prepare, but let's do it live. Okay, AA, let's go. So these are essentially AA, I believe AA proofs. All right. So maybe I'll get stuck along the way. So I hope you all can help me. So let's try this one, right? The second one. Okay, the first one, I think, right? If, okay, two directions, okay. Two directions. So first, if you start from the right-hand side, generated by homogeneous polynomials, right? That would imply that ideal is graded. Why? Because, right, you use the homogeneous components to generate the ideal itself, right? So how should I write it out? So maybe F1, F2 are all homogeneous, okay? And then right, since they're all homogeneous, so and then what so suppose a random polynomial is inside this ideal, right? It will be a combination of these fn's and then multiplied by the original polynomial ring. Okay, so that will imply, can I just go over, like, because okay, like since they are all homogeneous, right, that will imply the homogeneous components are all also in the ideal itself. Why? Because, like, for example, maybe you have something like f1, where f is equal to sum of r, ri, fi, okay, and ri is in the original polynomial ring. So what we want to show is that fd is also inside also inside the ideal itself. Okay, yeah, okay. So so like for example, like how do you go? So because these are all homogeneous, when you multiply out with the random R1s, right? Those parts will also be right inside the original ideal itself, right? By definition of the ideal. So that's why it's also in there, right? I hope because I'm lazy to write the line out, but I hope that's clear that way, because like when you multiply it out, right, those components are also like inside the original ideal, because you're just multiplying by from the ring of the polynomial ring. So that's why FD is also inside the original ideal. Yeah. By the way, like the book says these proofs are obvious. So I mean, some sense it kind like it's just like a standard AA practice. All right, that's for the okay. I mean, the book says it's obvious. Yeah.
Reason why
Yeah.
all the things.
Yeah.
So when someone thinks that it's obvious, try to write down the definition on both sides,
Yeah.
and that should be easily seen there.
Yeah.
Yeah, no need having extra work done.
Yeah. Yeah. So you just need to write down the definition, and they naturally relate to another like that. Yeah. Yeah. So that was the case, because yeah, when you multiply out all those RIFIs, they also are inside the original ideal itself. So, and then therefore it's graded. For the other direction, I'm not sure. So if the ideal is graded, then it is generated by a homogeneous a set. Oh, this sounds more longer to prove, but I don't know, right?
Just for every polynomial in this idea, I'll take all the homogeneous, how do you call it? Like if f is
The homogeneous components.
yeah, take all homogeneous components
Mhm.
and then take all of them for all the polynomials.
Yeah.
It clearly generates the whole ideal, because now you take any polynomial from your ideal, so you have added its homogeneous components to the generating set. So
Yeah.
of course it is this.
Yeah. So and then yeah, but you need to make sure it's finite and it's finite. Oh, sorry. Yeah, it's generated. Yeah. Oh.
Even the proof is finitely generated.
I mean, yeah, it is finitely generated, but
Yeah.
okay, it's not saying that it's generated by finitely many homogeneous polynomials,
Yeah.
right? Probably that's also true, but
The property in the book says finitely.
Yeah.
that's it.
Yeah.
Okay.
It should be finitely.
Yeah,
That's further work.
yeah, I think it's true. Just take for the generators, take all the homogeneous components and
Yeah. The homogeneous components, right? They should be finite. In what way? Like, yeah. Yeah.
if you start with idea generated by like F1 to Fn, just take homogeneous components of all those polynomials. It's still finitely many of them. Yeah, and they certainly, in the idea generated by them, you have F1 and Fn. And also the other way around. Yeah, by homogeneity, also those components are in the idea generated by F1 to Fn.
Mm. Yeah. Yeah, I'll probably append the details later. Okay. So, yeah, but you can reduce it, like, Hilbert base. So, but anyway, so, where do you go? Yeah, so the second statement is the radical ideal, right? Is a graded, of a graded ideal is still graded, right? So, like, okay. All right. So if, like, for example, you're in F, okay. So if it's the original radical ideal is graded. So okay, writing out definition like F, right? And then like for R and N, and then so on. Then FR is inside that ideal. Okay. Okay. So. So A is originally graded, so that means FD is all in A. Okay. But at the same time, since you're raising it to a power, the FDs are also there. So, oh, okay, maybe next time should write it out more. Okay, so like, okay, right, F is in, right, F in A implies, right, F E implies in A implies F E is also in A. Okay, right, so, right, so what we want to show, okay. Yeah, and yes, yes, okay, right. Right, we still got time. What? Skippable. So, okay, looks like, uh, well, last time when we had proofs like this, we also kind of skipped it. Okay, like for example, this one, hmm? What?
Because you are actually taking our roots
Yeah,
back, right? And so you want to prove that radical is greater, right?
yeah,
So you just follow that definition.
yeah,
You just check that for every component in A. So now your A becomes square root A, right?
yeah,
And you're going to check that all the homogeneous components also is
yeah, yeah,
the random value.
yeah.
So to check that so you backward lah, you do
Yeah.
backward reasoning lah.
Okay, sure.
So you want the FE to live inside the radical A, meaning what? You want the somehow of it live inside A, and then you somehow need to use the A being greater, right?
Yeah,
And to argue that.
it's B.
Yeah, I mean just spell out or
Yeah, so, yeah, that would imply that F to the R is also in A for all R. And then, F and R is in A, and F of D is also in A. And, right. Oh, yeah, P. And then, okay.
FRD in A. So you want FE in brackets A, right?
Yeah,
So imply that FER some R should be fitting in A, right? A, just FER.
I do.
Okay. And then, so you try the other direction also.
yeah.
So if F in red A, then that exists. And
And such a F of R.
okay, so now then you need so now they lead into graded idea already, right? So somehow you should use the graded definition here. So how the graded play like graded idea
Half of the graded. So and now. So the trick is that if F has homogeneous components F1 to Fd, let's say, then Fi to R will be a homogeneous component of F to R, because you cannot get the same degree by taking any other factors, right? So you just write, you write like F equals F1 to A plus 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 Fe, and then take the R power, and notice that F equals F1, yes.
Yeah.
And then if you look at the R power of this, then Fi to power R will be the only term of this degree. degree. You cannot get the same degree by taking that down. So you get that fi power r is a homogeneous component. So because the homogeneous components, by definition of being graded ideal, it will belong to A. And fi to r belongs to A.
Yeah.
And that means that I belongs to the radical of A. So,
Yeah, so just like write the definitions out and then, yeah, do it so on. Fi, Fi,
yeah, any component that I.
yeah, and component Fi, yeah.
To power r will be, yeah, it is a component of n r, so it must be the n.
Right, so,
Of fi is the radical.
but for all finding Fi,
Yeah,
yeah, the Fi is in the radical for any I because, yeah, okay, thank you. Yeah, okay, so, alright, so it looks like, okay, maybe we need to write our definition and some.
yeah, but it's not just
Yeah.
not only playing with definition, but you also have to notice that they form the single graded components, right? Homogeneous components, yeah,
Yeah, to make use of the, yeah, alright, right, it's like, yeah, we lengthened it enough, so, yeah, so, okay, I'll pen this proof after the talk, okay, so, okay, shouldn't skip this proof, but the point of these properties is to show that they are still, these graded ideals still behave the same as the zero sets before. Yeah, so like we make use of zero sum products and intersections in the previous sections, and they remaining graded means our definition remains consistent. Yeah. Okay, all right. So, all right, that's the first direction. We have shown that it's graded. Okay, so that's one extra property that we need to have if it's an algebraic subset or Pn. So yeah, the corresponding ideal has to be graded. Okay, so that's the first direction, right? The second direction, I, right? We instead of straight away going back, because since for projective spaces we define it dimension up. So this is how we're going to do it. So but basically it's still the same idea as before. So we for all projective planes or spaces, right? You can identify it with a cone in the higher dimension, the n+1 higher dimension. So here's a short animation. So right, this is yeah, the projective plane, and then we are okay, just watch it move. So over here the dark lines are the projective the algebraic curve on the projective plane, and then these perspectives, these lines are all the corresponding lines in the higher dimension. So in fact, so at least this is the general definition of a cone. Although when you think of a cone, I usually think of a simple circular cone like that. But over here, right, the definition of cone is also natural. So it's like something like if a point is inside the cone, right, then that would imply that C, for any C, for all C, right, in, I guess, the field, the degree field, and then CV is inside the cone too. All right. So this is the same thing from perspective. So at least you can see from here, like the algebraic curve in the projective plane is identified with the cones, okay, in higher dimension. So, right, this is, so essentially what I did just now is what this is saying, right? Pi defined earlier, like is like how we identify the space, the fine space in a higher dimension with the projective space with one dimension less below. So this pi is standing, or this pi is like, for example, Pn is over here, and then the higher dimensional space over here, K the n plus 1. Okay, so pi sends it in this direction, right? Maps it that way. So doing the inverse process, right? The pre-image. So sending it this way is equivalent to like contracting all these lines onto the plane. Okay, so the inverse process, the pre-image will be just taking the pre-image of the S inside the projective space and then just projecting it out and then forming the cone. So and then you also have to include the origin as that because we disclude we disclude the origin from the higher dimensional space. So with that, we can define the ideal of a projective algebraic subset of Pn. Okay, so the ideal of an algebraic subset of Pn, right, corresponds to the polynomials that equal 0 on this space on that cone, which actually also correspond to the homogeneous polynomials. Yeah, so but essentially that is doing the exact same thing as I above. So we managed, okay, this is how we go back, right? From algebra geometry from algebra geometry and I from geometry to algebra. And then, okay, this is one last question mark. Okay, one last question mark to settle, which is settled by this remark. Okay, this is what we did last time. Essentially, what we did last time. So like the zero sets satisfy these properties, and then they with this we can define the Zariski topology. But so essentially, all those proofs just over here is the same as in week 1. And then it's just utilizing the relation between V and V affine. But okay, one interesting part is this part, right? When V of the ideal, the zero sets of the ideal is equal to 0, is equal to the empty set, right? So when V, the zero sets of an ideal is equal to the empty set, right? What does that mean, right? That means that like when you go back to the fine space, right, it is I only equal just less than subset of the origin. Like why? Because I go back here to the original definition, right? Over here. So when you take the code, when you quotient it by the equivalence relation, right? V affine, you take out the origin and then you quotient it. So essentially all those lines are, since you say it's an empty set, all those lines are gone. So the only thing you are left with is the origin. So since you're only left with the origin, right? You're only left with the origin. So, okay, consistent, right? And then we just apply the Nustellensatz from before, right? Since this is in a fine space, the high dimensional space n plus 1, it's all fine. So we just go back the other direction, right? It's applying I on both sides, I guess. So applying idealizing it from both sides, and then because it's inclusion reversing, so we reverse the inclusion. We have that this becomes radical, right? Because I and V are fine, right? Since like the bijection defined by Nustellensatz, right? This just ends up becoming a radical. And then radical of the ideal, right? It's just that is larger than these ideal generated by x naught up to xn. So so it's interesting because it's not the whole polynomial ring. Okay, it's not the whole polynomial ring. So in the past, this will correspond to k. A would just straight equal to the whole polynomial ring, but it's not this case because like of the homogeneous polynomials. So just to clarify, right, the ideal generated by these monomials x0 up till xn, right? Right, and then what is it missing from the whole polynomial ring, right? X0 to xn, right? Right, this polynomial ring still can contain constant terms just from K. Right, over here, it can't. Why? Because it is like all the sum by these x0 up to xn. So it has to at least be like contain these terms. The original polynomial ring doesn't. But in fact, if you do the same computations like just now, right, you find that vx0 up to xn and then v of the whole polynomial ring is all both equal to the empty set. So this is just a small problem that it causes, but so all we need to do is just add a proper meaning that the ideal is not the whole polynomial ring, these graded ideals. And with that, we have our original equivalent bijection again, right? Proper graded radical ideals for the polynomial ring correspond to the algebraic subsets of Pn. Oh, okay, so yeah, essentially, right, good, on time. So essentially, that's what this proposition states. And then, yeah, so like, just basically what they wrote in a few lines is, I mentioned just now, right? Although, of course, you need to check some of the details for the bijection, but essentially that's just the case, right, with these definitions. And then with that, you can define the bijection between algebra and geometry. So, okay, a small detail is the irreducibility, right? If you want to like continue on with projective variety, the irreducibility also transfers along. So, okay, right, example, right? Okay, I forgot about this. So, example of this bijection will be this, right? So we have a hyperplane. Oh, sure, capitalized. But we have a hyperplane, and then this hyperplane is defined by setting x0 to equal 0. So that means this hyperplane is the hyperplane at infinity. So what does this ideal the corresponding ideal this hyperplane? So on the geometry side, we have this hyperplane, right? This hyperplane over here, right? In this space, right? At infinity, of course, right? And then what's the corresponding ideal, right? That set it equals 0. Since it's quite can be seen from the condition set, just the idealization is just the thing generated by x0, right? And then so yeah, this ideal corresponds to this hyperplane at infinity, and then of course, okay, maybe this example more quite trivial, but if you try it with more interesting like non-linear polynomials, it will still work. All right, so right, good, right, on time. So basically, yeah, that's it. So yeah, conclusion, yeah, there's nothing really. So yeah, so projective space is good. Hopefully that was motivated at the front. And so naturally, right, the algebra, right, it's all about homogeneous polynomials, so it's also good. So yeah, we have further questions that we could discuss, right? We didn't define Zariski corner rings and so on. Okay, and then it's these implications and so on. So although I probably know, well, anyway, so yeah, we have a study group on Monday, Friday, Wednesday, and Saturday, Sunday, so you can come along and discuss. So that's all. Right, thank you all for coming. Yeah. Right. Oh, okay, sure,
It's
sure.
not exactly like that. It's almost like that. It's like if you have f is in the radical of A, so you have f to r is in A for some r, and then you write f as f1 plus fd, where this is the component of degree 1, component of degree 2, up to component of degree d. And then you raise it to power r. Okay, it's not true that fi to R will be a separate separate homogeneous component, but Fd to power R is a separate homogeneous component because it has the highest degree of all the monomials that you get from this. So you get, by the assumption that A was radical, you get that this belongs to A. So Fd belongs to A, and now you do induction. So you have proved that Fd belongs to A, so now you only have to show that F1, sorry, not to A, to the radical of A. So from this you have that F1 plus Fd minus 1 belongs to radical of A, yeah, because the whole thing F1 plus Fd belongs to radical of A, and now we prove that Fd belongs to radical of A. So you have this, so you have something shorter of smaller degree, and you do induction, okay? So it's not as quick as I thought initially, but it's pretty close.
Just the idea.
Nice.
Yeah, thank you. Thank you. Right, now it's fine. Thank you.